Today we are going to learn about CNN optimization, techniques for improved performance. By the end of this video, you'll be equipped with strategies to enhance the accuracy and efficiency of CNN models using key optimization techniques.
Welcome to our video on CNN optimization, techniques for improved performance. In this video, we'll explore various strategies you can employ to enhance the performance of convolutional neural networks, CNNs. Optimizing CNNs is crucial for improving both the accuracy and efficiency of models in real-world applications. Through this video, you'll gain practical insights into fine-tuning CNN models to meet diverse task requirements.
CNN optimization is not just a buzzword, it is a foundational aspect of creating high-performing AI models. Optimizing CNNs leads to increased accuracy, ensuring that models make fewer mistakes and deliver more reliable results. In real-world applications, efficiency is equally important. Optimized CNNs run faster and require less computational power, which translates to reduced costs and improved user experience. Furthermore, optimization enhances the model's ability to generalize from training data to new, unseen data, making it robust and versatile. Finally, in a competitive landscape, optimizing CNNs can provide a significant edge, enabling AI innovations that stand out in terms of performance and reliability.
The learning rate is a critical hyperparameter in the training of CNNs, influencing how quickly a model converges to a solution. Learning rate schedules help adjust the learning rate during training, either manually or automatically, to ensure efficient convergence. There are various types of learning rate schedules, such as step decay, exponential decay, and adaptive learning rates like ATOM or RM-SPROP. Each approach has its pros and cons, affecting the speed and stability of training. By implementing a learning rate schedule, you can prevent overshooting the optimal solution and ensure a smooth path to convergence. Tools like TensorFlow and PyTorch offer built-in functions to easily apply learning rate schedules, making them practical for both beginners and experts. Dropout is a regularization technique used to prevent overfitting in neural networks, including CNNs. It works by randomly dropping out or ignoring a subset of neurons during each training iteration, which discourages the network from relying too heavily on any particular neuron. This randomness forces the model to learn more robust features that are generalizable to new data, thereby improving its overall performance. Implementing dropout is straightforward with libraries like Keras and TensorFlow, where you can specify dropout rates for each layer. However, it's important to balance dropout rates, as too high a rate can lead to underfitting. A typical range is between 0.2 and 0.5, allowing the model enough flexibility to learn while maintaining regularization.
Batch normalization is a technique used to stabilize and accelerate the training of deep neural networks, including CNNs. It normalizes the input of each layer by adjusting and scaling the activations. This helps in reducing the internal covariate shift, where changes in network parameters can disrupt the learning process. Batch normalization allows for higher learning rates and reduces the sensitivity to the initial weights. The result is a faster and more stable training process. Integrating batch normalization into CNN architectures is straightforward and significantly improves performance, as shown in numerous studies and practical applications. Tools like PyTorch and TensorFlow make it easy to add batch normalization layers to your models. Data augmentation is a powerful technique for enhancing the size and quality of training datasets. By applying transformations such as rotation, flipping, scaling, and cropping, you can create diverse variations of the original data, helping models become more robust and generalizable. Beyond simple transformations, synthetic data generation methods can augment datasets further, providing additional examples for the model to learn from. Data augmentation doesn't just improve model performance, it also helps in mitigating overfitting by exposing the model to a wide range of scenarios. Practical tools like Keras and Albumentations offer easy-to-use interfaces for implementing data augmentation, making it accessible for all levels of practitioners.
Transfer learning involves leveraging pre-trained models to improve the performance and efficiency of CNNs on new tasks. This approach is particularly beneficial when you have limited data, as it allows you to build on the knowledge already captured by models trained on large datasets. Transfer learning can significantly speed up the training process and improve model accuracy. There are two main strategies: fine-tuning, where you adjust the pre-trained model's weights, and feature extraction, where you use the learned features as input to a new model. Popular pre-trained models like VGG16, ResNet, and Inception can serve as excellent starting points for your transfer learning endeavors. Hyperparameters play a crucial role in the performance of CNNs, influencing everything from convergence speed to final accuracy. Tuning these parameters can be challenging, but it's essential for optimizing model performance. Common methods include grid search, which exhaustively explores parameter combinations, and random search, which samples a subset of possibilities. Automated tools like HyperOpt and Optuna provide sophisticated algorithms to streamline the tuning process, making it more efficient and effective. The goal of hyperparameter tuning is to find a balance between accuracy and computational efficiency, ensuring that the model performs well without unnecessary resource expenditure.
Confusion matrices are vital tools for evaluating the performance of classification models, including CNNs. They provide a detailed breakdown of correct and incorrect predictions, helping you analyze model strengths and weaknesses. A confusion matrix displays true positives, true negatives, and false negatives, offering insights into where the model might be struggling. This visualization is invaluable for identifying areas of improvement and fine-tuning the model further. Tools like scikit-learn offer easy-to-use functions to generate confusion matrices, allowing for quick and effective performance analysis.
Several tools and libraries are specifically designed to aid in the optimization of CNNs. Popular libraries like TensorFlow, PyTorch, and Keras come with built-in features for implementing optimization techniques such as learning rate schedules, dropout, and batch normalization. These libraries benefit from strong community support, providing resources, forums, and tutorials to help you optimize your CNNs effectively. Integrating these libraries into your workflow can significantly enhance your ability to fine-tune models and stay competitive in the rapidly evolving AI landscape. Keeping abreast of the latest updates and features in these tools ensures that you're leveraging the best practices in CNN optimization. In conclusion, optimizing CNNs is a critical step in developing high-performance AI models capable of tackling complex real-world challenges. From learning rate schedules to dropout, batch normalization, data augmentation, and transfer learning, each technique plays a vital role in enhancing model accuracy and efficiency. By applying these strategies, you can significantly improve your CNN's performance and applicability. We encourage you to experiment with these techniques in your projects and continue exploring the vast resources available for CNN optimization. Thank you for joining us, and we wish you success in your machine learning endeavors.